Module 3, Lecture B, Loops and Repetition. By the end of this lecture, you will be able to write for loops to iterate over sequences such as strings and ranges, create while loops that repeat until a condition is no longer true, and use break and continue to control loop execution in simple scenarios. For loops basics. Using range in loops. A range-based loop is useful when you want a loop to run a specific number of times or follow a predictable sequence. Instead of manually updating a counter, you define the range of values and the loop automatically steps through each one. This is helpful for tasks like simulating coin flips or sending reminder emails. Using a range-based loop makes the repetition in your code clearer and easier for you and others to understand. Using ranges and loops lets you choose where counting starts, where it stops, and how much it changes each time. This is useful for indexing lists or arrays, such as starting at 0 and stopping before a certain limit. You can also start from another value, like 1 for page numbers or 5 for the 5th day of an experiment. By adjusting the step size, you can skip values, for example, to count by 2s or 10s. Overall, controlling the start, ending, and step makes it easy to design loops that match your specific task without extra complexity. Ranges and loops do more than simple counting. They connect abstract iteration to real tasks. They let you process ordered data, such as hourly temperatures, monthly financial records, or evenly spaced positions in graphics. The range defines how many times the loop runs, while the loop body defines what happens at each step. Learning to control the start, end, and step size of a range is essential for building efficient loops that match the structure of your problem. Python code. Using range in loops. Show how to use the range feature to repeat simple actions several times. Clearly demonstrate how changing the starting value, ending value, and step size affects the sequence of numbers it produces. Print the results so beginners can easily hear and understand how different range settings change the output. This comment explains that you do not need to run any pip install commands for this script because it only relies on Python's built-in features. In other words, the code does not use any external libraries. This keeps the script simple, easy to run, and accessible for anyone with a standard Python installation. In this example, we use a for loop together with the range function to repeat an action a specific number of times. Calling range with the value 5 produces the numbers 0 through 4. The loop goes through each of these numbers in order and prints a message that includes the current number. This shows how range conveniently creates a simple sequence starting at 0, which is a common way to control how many times a loop runs in Python. This loop counts through a sequence of numbers starting at 1 and stopping before 4. For each number, it prints a message showing the current count. It illustrates how to use a range with a custom starting point instead of beginning at 0. This is useful when zero-based counting does not fit the situation. This part of the code shows how to use a range with a custom step size. It creates a loop that starts at 0, goes up to, but does not include 13, and increases by 3 each time. During each loop, it prints the current value, which represents each step in the range. This technique is useful when you need to handle data at fixed intervals, such as measuring every 3 inches. This script shows how the range function controls loops in Python by changing where counting starts, where it stops, and how big each step is. It first counts from 0 to 4 to demonstrate the default behavior, starting at 0. Then it counts from 1 to 3 to show how to choose a different starting value. Finally, it counts by threes from 0 to 12 to illustrate using a custom step size. Each loop prints the current number so you can clearly see how the range settings affect the sequence of values. Looping over strings. When you loop through text, you tell the computer to handle each character one after another in order. Because text is an ordered sequence, the loop starts at the first character, performs the chosen operation, then moves on until it reaches the end. This means you can apply the same action to every character without manually keeping track of positions. Whether the text is a word, a sentence, or a paragraph, the loop systematically processes each character from start to finish. Looping through text lets you apply the same check or action to every character in a string. This is useful for counting letters in a name, looking for unwanted symbols in a form, or counting specific letters like vowels in a sentence. You can also use it to verify product codes or scan logs for warning symbols. In all these cases, the loop systematically processes each character to support tasks like inspection, filtering, and transformation. When you loop over text one character at a time, you can decide whether to keep, change, or skip each character to build new text. This lets you clean a message by removing spaces and punctuation, or convert a title to lowercase as you go. In data tasks, you can also pull out digits from comma-separated values or replace symbols in a paragraph with clearer alternatives. Overall, looping through characters gives you precise, predictable control over how the final text is formed. Python code, looping over strings. In this lesson, you will see how to loop through each character in a simple text string so that every character can be examined and, if needed, transformed. As you process the characters one by one, you can apply rules such as converting them to lowercase or filtering out unwanted symbols. By the end, you will know how to build a cleaned, all-lowercase version of a short message using this character-by-character approach. This line in the script is simply a placeholder to remind you to install any libraries the code might need. It helps ensure that all dependencies are set up before you run the program. In this particular script, no external libraries are actually required, so the line is not functionally necessary. However, including it reflects good practice for scripts that may later depend on additional packages. We begin by creating a variable that stores the text "Hello USA," which will be our original message for this example. This message includes uppercase letters and a punctuation mark. These features make it useful for showing how we can process and transform each individual character in a string. We begin by printing the original message to the console so we can see the string before any changes are made. This gives us a clear view of the initial state of the data we are working with. It also provides a simple way to verify that we have the correct input. Finally, it serves as a reference point for comparing how the message looks after we process or modify it. We begin by setting up an empty string called the cleaned message, which will hold only the characters we decide to keep from the original message. Starting with an empty string gives us a fresh place to store the processed result. As we later loop through each character in the original message, we will add only the characters that meet our conditions to this cleaned message. This approach helps us gradually build a filtered version of the original text. We process the original message by looping through it one character at a time, so we can examine each character individually. For each character, we decide whether it should be included in a cleaned version of the message. This selective evaluation lets us transform and rebuild the string based on specific rules, such as keeping only letters and digits. In this way, we construct a new, filtered message from the original text. The code checks whether the current character is a letter or a digit using built-in tests that return true for alphabetic characters and true for numeric characters. If either test succeeds, the character is treated as valid. Only characters that pass this check are allowed to move on to further processing. In this part of the code, each character that is recognized as a letter or a digit is converted to lowercase to keep the text consistent. This uniform lowercase format makes the data easier to process and compare later on. After conversion, the lowercase character is added to a growing string. That string will eventually contain the cleaned and processed version of the original message. The final step of the program is to print the cleaned message. This message is created by taking each character from the original text, converting it to lowercase, and removing anything that is not a letter or number. The print command then shows this transformed version so we can see the end result of the cleaning process. This script scans through the message, "Hello USA," character by character, and keeps only letters and digits. For each of these characters, it converts them to lowercase and adds them to a new string. Any spaces, punctuation, or other non-alphanumeric characters are skipped. The final result is a cleaned, lowercase version of the original message, which in this example becomes "Hello USA," showing a simple way to filter and transform text data. Loop counting techniques. When you use a loop to count, you are both repeating an action and keeping track of how many times it occurs. This is a common reason to use loops, such as processing a fixed number of items or simulating a set number of steps. A loop starts from a known value, changes in a predictable way, and stops at a defined point. Learning this counting pattern and how to adjust it for different situations is essential for using loops accurately and reliably. A key advantage of loop-based counting is that you can control where the count starts, where it ends, and how much it changes each time. This lets you match the loop to the structure of your problem, such as days in a month, even positions in a list, or weekly workdays. In data analysis, you might look at every 10th measurement to see trends more quickly, and in user interfaces, you might use larger steps to place labels along a timeline. By choosing the start, stop, and step carefully, the loop becomes a precise tool for working with days, seats, animation frames, and many similar tasks. When you use a loop to move through positions in a structure, such as characters in a string or items in a list, it is important to choose the starting value of the counter carefully. The loop's counter connects the idea of the next item to its actual position, which you might say aloud, label, or use in a calculation. Starting the count at 1 often makes more sense for people, while starting at 0 usually matches how internal systems work. By deciding how the loop counts from the beginning, you help your program track its progress in a clear and meaningful way. Python code, loop counting techniques. We will demonstrate how loops count using different starting points, ending points, and step sizes. You will see how each count lines up with positions in a simple sequence, so it is clear which number comes at each step. The results will be printed in an easy-to-read way, helping beginners recognize and understand basic counting patterns in loops. This line is simply a comment explaining that pip install commands are not needed for this example. It tells you that the code does not depend on any external libraries that must be installed. As a result, the example remains simple, self-contained, and easy to run for demonstration purposes. We use a loop to count from 1 to 5 by defining a range that starts at 1 and stops just before 6, increasing by 1 each time. The loop goes through each number in this sequence in order. During each pass, it prints the current number as the day number. This creates a simple, clear counting pattern from day 1 through day 5. We print a simple separator line made of 3 dashes to clearly divide different sections of the program's output. This visual break in the console helps distinguish where one part of the code's results ends and the next begins. Using such separators makes the output easier to read and understand, especially when multiple operations or steps are being displayed. We use a loop that starts at 2 and goes up to, but not including 12, increasing by 2 each time. This means the loop visits only even numbers in that range. For each of these numbers, we print a message that it is an even seat number, followed by the number itself. This shows how choosing a step value in a loop lets us skip unwanted numbers, in this case, the odd ones. We print a separator line made of 3 dashes to clearly mark the boundary between sections of the program's output. This visual break helps distinguish the results of different counting techniques shown in the code. By separating these sections, it becomes easier for someone reading the output to follow the transitions and understand which results belong to which method. We create a variable called product code and give it the string value AB9X. This value represents a simple product identifier. Storing the string in a variable lets us easily use it later. For example, when we want to work with each character in the sequence or match characters to their positions. We use a loop with a range of numbers from 0 up to the length of the product code, so we can visit each position in the string. At each step, the loop gives us an index, which we use to access the character stored at that position. We then print the index together with its corresponding character. This shows how each character in a string is aligned with a specific index, making the relationship between positions and characters clear. This script demonstrates 3 ways to count using loops. It first counts from 1 to 5, labeling each value as a day number to show a simple sequence with a step of 1. It then counts even numbers from 2 to 10, showing how changing the step to 2 skips the odd numbers. Finally, it goes through each character in a product code string, then pairs it with its position, illustrating how to access elements in a sequence by their index. The sections are clearly separated, so you can compare these different counting patterns. While loops basics, understanding loop conditions. When working with while loops, the most important part is the loop condition because it decides whether the loop continues or stops. You can think of it as a yes or no question that keeps repeating actions as long as the answer is yes. This condition usually depends on changing values, such as a counter or user input, like repeatedly asking for a password until it is correct, or running a simulation while a temperature stays above a threshold. The key is to design the condition so it accurately represents when to proceed and when to halt, preventing the loop from running too long or stopping too early. When designing loop conditions, first, imagine the desired end state and then define a clear condition that becomes false when that state is reached. Think about exactly when the loop should stop, such as when there are no packages left to scan in a warehouse or when a bank account balance drops below a certain amount. As the loop runs, it updates the relevant values, and once the condition is no longer true, the loop ends. This tight link between the changing state of the program and the loop condition lets you control ongoing processes in a precise way. When designing loop conditions, it is important to understand whether they are simple or compound, because this affects how easily you can predict the loop's behavior. A simple condition might just check whether a counter is below a limit, while a compound condition might check several things at once, such as whether a user has not quit and there are still tasks or questions remaining. In an online quiz, for example, the loop might continue only while there are unanswered questions and time is left. Aim to make your loop conditions closely match the real-world rules you are modeling, so you can clearly see how they change during each iteration and ensure the loop stops at the correct time, producing reliable results. Python code. Understanding loop conditions. Explain how while loop conditions control how many times the loop repeats, and show how a changing value inside the loop eventually makes the condition false, so the loop stops on its own. Use clear numeric examples to illustrate this changing state. Also compare loops that use a single simple condition with those that use compound conditions, such as combining two numeric tests, so learners can see how different conditions affect when the loop continues or ends. This line is a reminder to install any required external library before running the script. It represents a command you would normally run in a terminal to make sure all needed dependencies are available. In short, it tells you to verify that any libraries the code relies on are properly installed so the script can function correctly. We start the simulation by setting an initial temperature in degrees Fahrenheit, which serves as the starting condition for the cooling process. This initial value acts as the baseline from which all changes are measured. As the simulation runs, the loop uses this starting temperature to track how the temperature decreases over time. Defining this starting point is essential for observing and analyzing the cooling behavior throughout the simulation. We set the threshold temperature to 75 degrees Fahrenheit, which defines when the loop should stop. The loop keeps running while the current temperature is above this value. In effect, it simulates a cooling process that continues until the environment reaches this comfortable temperature level. In this simulation, the cooling rate is set to 3 degrees Fahrenheit per minute. This means the temperature is programmed to drop by that amount every minute. The value stays constant throughout the process, ensuring a steady and controlled decrease in temperature over time. We begin by setting the current temperature to the initial value defined earlier, so the program has a clear starting point. This initial value is essential for the loop that follows, because it lets us track how the temperature changes over time. By initializing the temperature in this way, the loop can compare it to the threshold and properly simulate the cooling process. We begin by creating a counter to measure how many minutes have passed during the cooling process. It starts at 0, meaning no time has elapsed at the beginning. As the loop runs, this counter increases by 1 each minute. This lets us keep track of the total cooling time as the process continues. The code first prints a short header message that introduces the simulation. It tells the user that the program will show the temperature at each minute. It also explains that this will continue until the temperature reaches a comfortable level. This message sets the context so the user understands the purpose of the simulation and what the upcoming output represents. The code uses a while loop to keep checking whether the current temperature is still above a set threshold. As long as the temperature is higher than this threshold, the loop continues to run. Each time the loop runs, it represents 1 minute passing in the simulation while the temperature gradually drops. The loop automatically ends when the temperature reaches or goes below the threshold, meaning the cooling process has reached a comfortable level. This line of code increases the minutes counter by 1 to represent the passing of another minute in the simulation. It keeps track of how long the cooling process has been running. By updating this counter each time, the program can later report the total number of minutes that have passed since the loop began. Each minute, the current temperature in Fahrenheit is decreased by a fixed cooling step. This repeated subtraction models a gradual cooling process over time. As the temperature is reduced, it moves closer to a set threshold. Once the temperature drops below that threshold, the loop condition becomes false and the loop stops running. This code prints the current minute and the temperature in Fahrenheit at each step of the loop. By watching these values, we can see how the temperature changes over time. This lets us track the cooling process and understand how the loop's stopping condition changes with each iteration. The final print statement announces that the cooling process has stopped because the loop condition is no longer met. In other words, the current temperature is no longer above the threshold. This message confirms that the temperature is now at a comfortable level and marks the end of the simulation. This script models a cooling process using a while loop. It begins at 90 degrees Fahrenheit and reduces the temperature by 3 degrees each minute until it drops below 75 degrees. At each step, it reports the elapsed time and current temperature so you can follow the cooling trend. When the temperature reaches the comfortable threshold, the loop ends and a final message confirms that the temperature is now comfortable. This illustrates how a simple loop condition can control repeated actions based on a changing value. Sentinel values explained. In many loops, you keep repeating steps until a certain condition changes, and a common way to do this is by using a sentinel value. A sentinel is a special value that does not represent normal data, but instead marks the end of useful input or processing. For example, when entering exam scores to compute an average, a negative number can serve as the sentinel because it is not a valid score. The loop processes all valid scores and then stops as soon as the sentinel value is entered, indicating there is no more data to handle. Sentinel values are special markers used in loops when you do not know in advance how many times the loop should run. Instead of counting a fixed number of iterations, the loop keeps processing input until it encounters this distinct value. For example, a system might record call durations or temperature readings until a unique marker signals the end of the data or a maintenance point. Because the sentinel is different from any normal data value, it clearly indicates when the loop should stop. A sentinel value is a special value used to signal when a loop should stop, so it must be chosen so it can never be mistaken for real data. For instance, a negative number can mark the end of age data since ages are 0 or higher, and specific words like quit or exit can end a menu loop. In financial systems, a reserve account number might serve as the end marker. By picking a clear, impossible as data sentinel, the loop runs only as long as needed and stops cleanly when that value appears, which makes the program easier to understand and maintain. Python code Sentinel Values Explained. This lesson explains how to use a sentinel value in a simple while loop to control repeated user input. A sentinel is a special value that signals when the loop should stop, allowing the program to end input safely without confusing the stop signal with real data. The example shows how to keep actual user data separate from the sentinel marker so the program only processes valid entries. Is needed, you may also install any required library before running the code that demonstrates this behavior. We use a sentinel value as a special marker to signal the end of input. In this example, -1 is chosen because it does not overlap with valid exam scores, which are non-negative. This makes it easy to tell the difference between real score data and the instruction to stop reading more input. By checking for this sentinel, the program knows exactly when to stop processing scores. We begin by setting the total score to 0, so it can store the sum of all valid scores the user enters. We also set a counter for the number of scores to 0 to track how many valid scores have been provided. These starting values are essential because they give us a clear baseline for both the total and the count. With these in place, we can later calculate the average score accurately. The program first shows a message telling the user to enter exam scores as percentages. It also explains that typing -1 will end the input. This -1 value acts as a sentinel that tells the program when to stop reading scores. By giving this instruction up front, the user knows both how to enter data and how to finish the process. The code is designed to work even when standard input is not available. It first tries to prompt the user for a score, expecting an integer value. If this attempt fails because input is not possible, it falls back to a predefined list of sample scores. This list contains typical scores and ends with a sentinel value of -1 to mimic user input. The code then takes the first score from this list to start the loop that processes these fallback values. The loop keeps running until the user enters the sentinel value of -1. For each valid score entered, the program adds that score to a running total and increases a counter that tracks how many scores have been entered. This way, every valid score affects both the total and the count. These two values are then used later to calculate the average score. The code tries to read another score from the user, asking for either a score or a special sentinel value to stop. It uses a try block to convert the input to an integer, and if this fails, for example, in an environment without standard input, it switches to a predefined list of sample scores. Each time an exception occurs, it moves to the next sample in the list and uses that as the input. If it runs out of sample values, it assigns the sentinel value, so the loop will end. After the loop ends, the program checks whether any valid scores were entered by seeing if the count of scores is greater than 0. If there are valid scores, it computes the average by dividing the total of all scores by the number of scores, and then prints this average along with how many scores were entered. If no valid scores were provided before the sentinel value, it simply tells the user that there is nothing to average. This script shows how to use a sentinel value to safely end a loop that collects user input. It repeatedly asks the user for exam scores and uses -1 as a special value that signals when to stop. Each valid score is added to a running total, and a counter tracks how many scores were entered. When the user enters the sentinel, the script checks whether any valid scores were provided, and, if so, calculates and prints the average. If no valid scores were entered, it simply reports that there is nothing to average, keeping the input handling clear and controlled. Preventing infinite loops. When using while loops, it is important to make sure they eventually stop running. A while loop continues as long as its condition is true. So if nothing changes that condition, the loop can run forever and freeze your program or waste resources. To prevent this, each loop iteration should make progress toward making the condition false, such as by updating a counter, processing data, or reacting to user input. By planning in advance how the loop will end, you greatly reduce the chance of creating an infinite loop. To avoid infinite loops, mentally step through your loop and think about how its state changes over time. If a loop keeps checking something, like unread messages, but never updates their status, it will run forever. The same problem occurs if a loop waits for a sensor value to change but never triggers a new reading. By simulating several iterations in your head, you can spot where the loop stops making progress and then adjust it so that each pass updates the necessary variables or state and moves closer to completion. When using loops, it is wise to add safeguards in case something goes wrong. You can set a backup condition, such as stopping after a certain number of iterations or after a set amount of time, even if the main task is not finished. For example, if a loop is trying to connect to a service, you might limit how many times it can try before reporting an error. In interactive programs, you should also give users a way to stop a loop, such as a cancel option. These measures do not replace correct logic, but they add extra protection so your program does not get stuck indefinitely. Python code, preventing infinite loops. This lesson shows how a while loop progresses safely by updating a counter each time it runs, so the loop eventually stops. It explains that without proper updates, a loop can run forever and cause problems. To prevent this, we add a safety cap that forces the loop to end after a certain number of iterations. Together, the counter updates and safety cap demonstrate basic techniques for avoiding infinite loops. In this part of the code, we point out that no pip install commands are needed for the example. This means the script does not depend on any external libraries that require separate installation. As a result, the code is simple, self-contained, and easy to run. Anyone using it only needs a working Python environment with no extra setup steps. We begin by setting the number of unread messages to 5, which serves as our starting count. This initial value lets us track how many messages still need attention. With the variable initialized, we can use a loop to repeatedly check and update the count. This process allows us to safely manage and gradually reduce the number of unread messages over time. The loop runs only while the number of unread messages is greater than 0, but still below 20. So it processes messages while also guarding against an unusually high count. During each pass through the loop, it reports the current number of unread messages. This provides simple feedback on the loop's progress as it continues to run. This line reduces the number of unread messages by 1, which is essential for the loop to move toward completion. Each time it runs, the unread count gets smaller. Eventually, this allows the loop to reach its exit condition and stop. Without this decrease, the loop could continue running indefinitely. The code uses a safety check that stops the loop if the number of unread messages reaches 20 or more. This condition suggests the loop might be running without end. When it triggers, the program prints a message explaining that the loop was stopped early because of the safety cap. This prevents an infinite loop and keeps the program under control. The code finishes by printing the final number of unread messages after the loop and any safety checks are done. This final value shows how the loop changed the unread messages count. It also confirms that the loop has completed and that any safety mechanisms have been applied if they were needed. This script uses a controlled while loop to process unread messages starting from 5. The loop runs only while the count is greater than 0 and less than 20, and each time through, it decreases the unread count by 1 and prints the new value. This design ensures the loop moves toward completion instead of running forever. If the unread count ever reached 20, a safety check would stop the loop early and print a warning. At the end, the script reports the final unread count, which should be 0 unless the safety limit was triggered. Loop control basics. Breaking out of loops. Breaking out of a loop means stopping it before it finishes all its repetitions. You do this when a certain condition is met, such as when you are searching a list for a specific ID and you have already found it. Ending the loop early saves time and computing resources because the program does not keep checking unnecessary items. It also makes the code's purpose clearer, since it shows exactly when and why the loop should stop. Breaking out of a loop is based on a specific condition that marks an important event in your program, such as finding a search target or detecting invalid data. When this event occurs, a break statement stops the loop immediately and moves control to the next part of the program, instead of waiting for the loop's normal condition to fail. This avoids unnecessary work and makes the program's flow match real-world logic, like stopping a search once a document is found or ending calculations when a risk limit is reached. Knowing when to break out of a loop is important for writing efficient, responsive programs. In interactive applications, you may need to stop a loop if the user cancels an action or a sensor reports an error. In data processing, you might break when a special marker appears so you avoid extra work. In algorithms such as searching or optimization, exiting early can greatly improve performance. Overall, breaking a loop is about deciding that continuing no longer supports the goal of your program. Python code: breaking out of loops. This section explains how to break out of loops early using a simple search example. When a loop is scanning through data to find a target value, a break statement can stop the loop as soon as the target is found. This is more efficient than letting the loop continue to run through all remaining items after the answer is already known. The comparison between running the full loop and exiting early with break highlights how this approach can save time and computation. If any external tools are required, they can be installed beforehand using the appropriate package installation command. We begin by creating a list of customer IDs that serves as a simple database. Each ID in the list is an integer that uniquely identifies a customer. Organizing the IDs in a list makes it easy to go through them one by one. This allows us to perform tasks such as searching for a particular customer ID efficiently. We set the target ID to 412, which is the specific customer ID we want to find in the list. This value defines the search condition for the loop that runs through all customer IDs. As the loop checks each ID, it compares it to 412. When it finds a match, the program knows it has located the desired customer and can then carry out the appropriate action. The code displays a message to tell the user that it is about to search the customer list. This message prepares the user for the next step in the program. It explains that the upcoming loop will look through the list of customer IDs. The goal of this search is to find a specific target ID within that list. We create a variable called found and set it to false to act as a flag during the search. This flag represents whether the target ID has been located while the loop runs. It starts as false because we have not searched yet and assume the target is not found. After the loop finishes, we can simply check this flag to see if the search was successful. We go through each customer ID in the list and compare it to the target ID we want to find. When we encounter a match, we report that the target ID has been found and that the search will stop early. At that point, we set a success flag to true and immediately break out of the loop to avoid any further unnecessary checks. After the loop finishes, the program checks the variable that tracks whether the target ID was found. The code prints a message to indicate that the search loop has finished running. This confirms that the loop has completed, whether it stopped early with a break or went through all its iterations. It also reassures you that the program is still running normally and has moved on to whatever comes after the search process. This script shows how to efficiently search for a specific customer ID in a list by using a loop that can exit early. The list acts as a simple database, and the loop checks each ID to see if it matches the target value of 412. When a match is found, the program prints a message that the ID was found and immediately breaks out of the loop to avoid extra checks. If the loop finishes without finding the target, it prints a message that the ID was not found. In either case, the program then continues running normally after the loop, illustrating how control flow proceeds once the search is complete. Skipping with continue. In loops, a continue-style control lets you skip the rest of the current iteration without stopping the loop. When a certain condition is met, the program immediately moves on to the next cycle of the loop. The loop itself keeps running as long as its main condition is true, but that particular iteration is cut short. This helps you avoid unnecessary work while preserving the overall loop structure. When processing a list of customer orders, some may be canceled and should be skipped to save time. A continue-style approach lets you ignore each canceled order and immediately move on to the next one, while still checking the entire list. This keeps the loop efficient and focused only on valid orders, such as when counting them or calculating total revenue. The same idea applies in other areas, like skipping invalid data in engineering or ignoring weekends in scheduling. When using a continue-style control in loops, you should place the skip check early so that, when a certain condition is met, the loop immediately moves to the next iteration and ignores the remaining steps for that item. This prevents accidentally performing actions, such as updating counters for data that should be excluded. It also keeps the logic clearer by separating the conditions for skipping from the main processing work. As a result, your loops become easier to understand, less error-prone, and more efficient. Python code, skipping with continue. This lesson shows how to use the continue keyword to skip unnecessary work inside a loop while still scanning the entire list of orders. As you iterate, you skip over canceled orders and only process active ones. You then print information about each processed active order and, after the loop finishes, report the final count of active orders. If needed, you can install any required library beforehand using the appropriate package installation command. We represent each order as a dictionary-like record that stores 3 pieces of information: an identifier for the order number, a status that tells us if the order is active or canceled, and an amount that gives its monetary value. By putting these records into a list, we create a simple structure that makes it easy to manage many orders at once. This setup lets us quickly process or filter orders based on their status and amount. We begin by creating 2 variables to track our results as we process the orders. One variable is a running total of the amounts from all active orders, starting at 0 as a decimal number. The other variable is a counter that tracks how many active orders we have seen, also starting at 0. Initializing these before the loop ensures they are ready to be updated each time we handle another order in the list. We loop through each order and check its status. If an order is marked as canceled, we announce that it is being skipped and immediately move on to the next order. By doing this, we avoid any further processing for canceled orders and ensure that only active orders continue through the processing steps. We process each active order by first printing a message with its ID and amount so we know which order is being handled. We then add the order amount to a running total to track the overall revenue from all active orders. Finally, we increase the count of active orders processed, which lets us later summarize how many successful transactions were completed. The code prints a summary of how many active orders were processed. It relies on a counter that is increased once for each active order during the loop. This final count shows how many orders were successfully handled. Any orders that were canceled and skipped are not included in this total. This code calculates and prints the total revenue from active orders. It goes through the list of orders, ignores any that are canceled, and adds up the amounts for the remaining active ones. The final result is a single total value that summarizes the revenue from all successfully processed orders. This script goes through a list of orders and ignores any that are marked as canceled. When it encounters a canceled order, it skips further work on that item and prints a message that it was skipped. For each active order, it prints the order ID and amount while updating a running total and a count of active orders. After all orders are processed, it reports how many active orders were found and the total revenue from them. This illustrates how the continue statement can be used to bypass unnecessary processing and focus only on relevant data. Nested loop fundamentals. Nested loops are used for complex problems where one repetition is not enough. The outer loop controls a broad cycle, while the inner loop handles repeated details for each step of the outer loop, such as multiple sessions within each day of a conference. It is important to understand this structure before using tools like break and continue, because these commands only affect the specific loop they are inside. Always be clear about which loop you are controlling, so the overall flow of your program behaves as you intend. In nested loops, it is crucial to know which loop a break or continue affects. For example, when checking rooms and their time slots, using break in the inner loop stops checking time slots for the current room, but lets the outer loop move on to the next room. Using break in the outer loop stops the entire search, such as when enough rooms have already been found. Similarly, continue in the inner loop skips only to the next time slot, while continue in the outer loop skips to the next room. This understanding lets you control the flow of nested loops effectively. Nested loops are useful for handling multidimensional tasks, such as scanning images or pairing students with projects, where one loop manages one dimension and the other manages another. Commands like break and continue can make these loops more efficient by skipping unnecessary checks or stopping once a good result is found. However, they only affect the loop they are directly inside, so you may need flags or careful conditions to influence outer loops. Building intuition for how these loops and controls interact will help you design efficient solutions for complex problems. Python code, nested loop fundamentals. This lesson uses classrooms and time slots to demonstrate how nested loops work together and how break and continue behave inside them. It shows that controlling the inner loop, such as skipping or stopping certain time slots, is different from controlling the outer loop, which moves between classrooms. By walking through these nested decisions, it highlights how each break or continue affects only its own loop level. Finally, it prints a small schedule summary that clearly explains why each classroom and time slot was included, skipped, or stopped. This comment explains that, although you could install extra libraries if needed, the current code only relies on standard Python. In other words, it is designed to run without any external dependencies. This makes the program easy to execute in any normal Python environment and keeps setup simple and accessible. We begin by setting up a list of classrooms that represents the different rooms in the building we want to schedule. We also create a list of morning time slots that represent the hours we can use for classes. These two lists let us systematically check each room at each time for availability. Finally, we define one specific time, 9 in the morning, as already booked to simulate a conflict. This lets us demonstrate how the scheduling logic detects and handles a time slot that is no longer free. The code starts by printing a header message to the console that explains what the program is about to do. It tells the user that the upcoming process will scan a classroom schedule using nested loops. The message also notes that control flow statements such as break and continue will be used. This introduction prepares the listener to see how these tools help manage classroom time slots within the loops. We go through each classroom in the list one by one, and, for each room, announce that we are checking it for scheduling conflicts. At the start of checking a room, we reset a flag that tracks whether we have found a suitable time slot. This flag is initially set to false and will only change if the inner loop discovers a time that works for that classroom. We loop through each time slot for the current classroom and check if it matches the double-booked time. If it does, we announce that this slot is skipped due to a conflict and immediately continue to the next slot, avoiding any further processing for it. If the slot is not double-booked, we mark that a suitable time has been found for this room and confirm that this is the first usable slot. Because we only need one valid slot per room, we then break out of the inner loop and stop checking additional times for that classroom. After the inner loop finishes, the program checks whether it found a suitable time slot for the current room. If no acceptable slot is found, it prints a message saying there are no suitable time slots for that room today. It then breaks out of the outer loop, based on the assumption that if one room has no available slots, the remaining rooms will also be unsuitable. This early exit avoids unnecessary checks and makes the process more efficient. At the end of the program, a final message is printed to confirm that scanning all the rooms with nested loops is complete. This message acts as a clear summary for the user. It indicates that the example using nested loops with break and continue statements has run and finished successfully. This script uses nested loops to manage classroom schedules and shows how break and continue control the flow. It loops through classrooms and their time slots, skipping double-book times with continue. When it finds an available slot, it prints a confirmation and breaks out of the inner loop so each room gets only one slot. If a room has no suitable time, it breaks out of the outer loop, assuming later rooms are also unavailable. The final output summarizes which rooms have open slots and where scheduling conflicts occur, illustrating nested loop behavior in a practical way. In this lecture, you learn to write for loops to iterate over sequences such as strings and ranges, create while loops that repeat until a condition is no longer true, and use break and continue to control loop execution in simple scenarios. In the next module, Module 4, we will go over data collections Thank you for your attention. See you all in the next lecture.